So great. I hope you can see my slides. So I'm talking exactly over astroparticle physics. In this case, I just put the emphasis of this talk a little bit more to cosmic ray observatories. So after the first speaker, we're talking about LHC. And in this case, I'm talking about cosmic rays and astroparticle physics, just a very quick reminder of what we're doing. So basically, we're measuring cosmic rays. And in this case, at the Pierre Observatory, where I'm currently working on, we study ultra-energy cosmic rays. So cosmic rays with energies at EeV, so 10 to the power of 18 electron volts. And you can see that at the very high energies, the number of particles which can be measured just drops immediately. So we have something like around 1 particle per 1,000 square kilometers a year at the very highest energies. And the idea is that we can find or try to find the sources, origins of these ultra energy cosmic rays. And so at very high energies, because of magnetic deflections, and the deflections become small, and also for small charges. So there are basically two important parameters one has to take care of, beside for sure a little bit other parameters, which are the energy and the charge. And we are measuring these ultra energy cosmic rays using their initiated air showers. So when the particles penetrate in the atmosphere of the Earth, they will induce such large particle cascades. And there's one specific property of this particle cascade, which is here the shower maximum, which is called Xmax. And this is the atmospheric depth of the shower maximum. And the shower maximum is defined via the part in the atmosphere where we have the largest number of particles. So the first, we have something like starting cascade. And then after the shower maximum, we have attenuation effects of the atmosphere, and the number of particles is decreasing. So when we are measuring cosmic rays, we can do it with several techniques. So using radius antenna, we can try to detect the radio emission of the air shower cascade provided through the atmosphere. We can use surface detector-based analysis of these shower particles, or we can use fluorescence telescopes to observe the longitudinal shower development. So the basic idea is that you can think of a cosmic ray observatory as such a very big calorimeter. So the atmosphere would then be the calorimeter material, and then the detector, such a particle detector on the surface, would just be a single readout layer. So this would be cosmic ray observatory in the nutshell for LHC. So the Pierre Observatory is the world's largest cosmic ray observatory located in Argentina, and the observatory covers an area of 3,000 square kilometers. And the main components of measuring ultra energy cosmic rays is the surface detector and the fluorescence detector. So you can see here the large area of the surface detector stations. You can see here one of the surface detector stations, and each of these black dots here is one of these surface detector stations arranged in a hexagonal grid, and with a distance of 1,500 meters. And then we have 4 different sites where we have fluorescence telescopes, 6 at each site, which can overlook the area, and we can perform hybrid measurements of cosmic ray-induced air showers. So it's very interesting to study these cosmic rays, and the 2 big challenges are to study the composition of the cosmic rays and also to search for the origins. And to reconstruct such air showers, we have these hybrid techniques. So if we have here such an impinging particle which is traversing the atmosphere, we can observe the longitudinal shower development using fluorescence telescopes. So we can directly measure the shower maximum, because we can just see, okay, at the shower maximum, there we have the largest number of particles in the atmosphere. And so the fluorescence light, which is emitted, is just larger at the shower maximum, so we can directly observe the shower maximum. And at the surface detector, we basically just measure here the footprint of particles, but the shower particle footprint is time dependent. So we have normally a shower front where we have like a high density of particles, which is then falling out with a larger radius and with larger times after the arrival time. And so the basic idea is, because up to now, this observation of the shower maximum is confined to fluorescence observations, which are confined to dark and moonless night. The duty cycle is very limited, and also the statistics. So the idea is to use deep learning to be able to reconstruct using the surface detector array, also the shower maximum Xmax. So why is the shower maximum such an interesting property? Because it scales with the number or with the mass of the particle. So normally you can study different moments of the shower maximum distribution, but basically the idea is when I show here the shower maximum and histogram here, the distribution for shower maximum caused or induced by iron, and for protons, I can see that for protons I have larger shower maximum, so the shower can penetrate deeper in the atmosphere, and we have something like a more heavier interactions for larger masses, and so we have smaller shower maximum, so less deep penetration for iron nuclei. And so we can see two things. First, that the mean of the distribution is shifted, and second, that also the width of the distribution is different. And because the mean is shifted and the distribution also has a different width, we can study with the first moment the average composition we measure for ultra energy cosmic rays, and with the second moment we also can get a feeling for the composition mix. And here we can see such of the measurements performed by the Pierre Observatory from 10 to the 18 eV to 10 to the 20 eV, and we can see here this line indicates or the red lines indicates the expectations for protons for various theoretic models called hadronic interaction models, and for blue you can see the lines for the iron nuclei. And we can see that for very large energies, especially the second moment, it's very challenging to measure, because measuring the second moment, for sure, we need a bit of statistics. And so it's quite interesting to get new insights in the cosmic ray composition, especially at the highest energies. But because here the statistical uncertainties just dominate the measurements. So the idea is to detect these air showers. So when we have an air shower just hitting our surface detector stations, in each of the stations, which are water Cherenkov stations, we can measure such time-dependent signals. And the idea is to perform something like speech recognition to these time-dependent signal traces. And because we have a clustering in space on our hexagonal surface detector array, the idea is to process these structures just like images. And we can perform this reconstruction using a special setup, because we have not only the signal traces and the position of the detector stations, but also the arrival time. So this is basically when the first shower particles arrive at each of the stations. And so we put everything into this new network to reconstruct the shower maximum Xmax. And this network is chosen as follows. We have a first part which focuses on these recount neural networks and the signal traces. So we have one RNN part, which consists of bidirectional LSTM, so long short-term memories. And they reconstruct out of these very long time traces, just 10 trace features. And this RNN part is shared over each of the stations. So each station just is analyzed by the same RNN. And then in the second part, we have a convolutional network, which uses these 10 features extracted by the recount network part, and also the arrival times. And another information is here given, which is just the station states, which just says, okay, is this station ready to measure or not? And because our surface detector array has a triangular structure or hexagonal structure, we use hexagonal convolutions. So maybe you know this convolution operation in 2D, we just use translational invariance and move these filters with the same weights over our feature maps. In this case, we have 6 more feature maps, or so-called orientation channels, because we not only perform a translation of the filter, but orientation channel cycling as well. So we just also use here 6 rotations of each of these filters. And finally, we then predict the single shower maximum value. And the network was trained using a large air shower simulation library, and the training on the GPU just took like 1 to 2 days. And the basic problem is that at the very highest energies, we cannot really know which interaction are happening and cannot precisely modeling the interaction at the highest energies. So we need to use phenomenologic modeling to describe these processes. And there are several of these theoretic models, hadronic interaction models, which are, let's say, that way on the market. And in this case, the neural network was trained on the EPOS LHC model, but there are just much more models. If you can have a look here on the reconstruction performance, we can see that we have overall no bias. So when we average among the compositions, and we have like a 10 EeV, only a small composition bias. So the difference between iron nuclei and proton nuclei is shown in red and in blue. And also we have the resolution shown as function of energy, which have an increased performance for higher energies. And just as a comparison, there's the delta method. So just a method based on a hand-based observable, where we can just use the signal traces and estimate the rise times, which can indicate the number of muon or the muon content of the shower. And the resolution of this delta method, this analytic approach, is 45 grams per centimeter square. So we can see that with these deep learning based methods, we can just really have a very, very nice performance. But there are several other things to compare with. So we have to evaluate it on additional interaction models. So here, for example, on the QGS model or the Sybil model. And what you can basically see is that the resolution is the same for all of the hadronic interaction model, but the overall bias, so you can see that here the reconstruction bias just moves downwards. So if we would average among all the composition, this is something like -5 grams. And for Sybil 2.3c, we would see it would go down for -15 grams per centimeter square. So we basically see that we have a dependency on the hadronic interaction model. So we need something to calibrate the performance of the DNN. So nicely, if you remember that we have these hybrid detection techniques. So there are showers where we have the surface detector measurement and also measurement from the fluorescence telescopes, which can directly and therefore precisely estimate the shower maximum. So we can basically just calibrate our predictions of the DNN to the Xmax scale of the fluorescence detector. And this is done here shown on this slide. So we can see first on the right side the correlation between the fluorescence telescope, the shower maximum reconstruction, and the DNN. And we can see a nice correlation of above 0.6, which is fine. And then we can see that the resolution matches the expectations. Just to remember that it slightly depends on the composition and just increases the performance with energy. So this looks good, but we can see that we have an over bias from around -30 grams per centimeter square. So now one can see that this bias does not depend on the energy. So we can just basically just fit a constant to this difference, and so calibrate our predictions to the scale of the fluorescence detector. And if we further would have a look on the systematics, but this is really ongoing, we can just calculate or estimate the expected systematics for really measuring using this DNN, the first and second moment of these Xmax distributions. And we can here see always as difference or as comparison the FD Xmax scale. So the very precise scale estimation is possible with the FD. We see that for the first moment, the scale is like just slightly larger. So we have a slightly larger systematic uncertainty for measuring the first moment using the DNN. And for the second moment, we can see that, the above 10 EeV, the expected systematics are something like -5 +5 grams per centimeter square, which is really good, because if you remember that in the beginning we have a look on the second moment, and the second moment, which is to expect it, lies something between 30 and 60 grams per centimeter square. So this can provide new insights into cosmic ray composition, but this analysis is ongoing. Then we saw that there was a bias of -30 grams per centimeter square, which is quite large. And so the basic idea is that for sure, if we do not know the real hadronic interaction model, this could cause some difference. So if we train our network on apples, we would have problems if we just try to reconstruct apples, but use different input data. And here the idea is that we in ultra energy cosmic ray community, we measure different muonic content of the air showers in simulation data. So you can see here the muon number or normalized muon number as a function of energy and the theoretic expectations in blue and in red. And we can see that we have a clear deviation between our measurement and the prediction of our hadronic interaction models. So the basic idea is that maybe this different performance is caused by different hadronic interaction models in nature and our description and simulation. So one idea could be that one uses a simulation where we have a specific electromagnetic part and muonic part, and we also simulate one data set where we just switch here the fraction. So this will definitely here change the shape of our signal traces. And this will have influence on our prediction. So if we train our network on simulation and evaluate it on simulation, we have a very nice performance. You can see here the energy in this case is very precisely reconstructed. But if we train it on simulation and evaluate it in data, we can see that the performance is just much worse. So the idea is that in the following, we use something like an adversarial framework for refine our simulation. So the idea is we put in the simulated traces and as a feedback, train this refiner, and then the refiner is able to refine the simulation to look more data-like. And this is done in the following adversarial framework. So we have something which is a little bit inspired from generative adversarial networks, but in this case, this really is a supervised or semi-supervised learning approach. So we put in some simulated data in our refiner network. Our refiner then tries to refine the simulation, gives out the refined simulation. And then we have a second network, the so-called critic network, here shown as a small professor, which then compares the refined traces or refined simulation to the real data we measure. And then our neural network, the critic network, will give feedback to the refiner how the refiner has to change the simulation that it looks more like data. And if we do this and refine the simulation, so again, the network trained on simulation but applied on data, we can see we have a bad performance. But if instead we train it on, not train the refiner in between, so we use the simulation, we use a refiner to refine the simulation, and then train the network on the refined simulation and evaluate it in data, we can see that we have a better, much better performance here. Okay, I think I have a little bit time more to talk about a different topic, which in this case is the identification of patterns in the cosmic ray arrival directions. So we first talked just about how to reconstruct out of really the low-level data some physics observables. And now in this case, the idea is that we would like to find the origins or sources of cosmic rays. And so when we collect our data, we have something like our data, which is just distributed on such a spherical data, because our Earth is just a sphere. So, and the idea is we would like to find the origins, and we set up such a simulation and would like to identify between different scenarios. So one scenario would be, okay, everything which just is measured by our observatory is just isotropy. So we cannot really measure sources because they're just so far away. And the other would be that maybe we have other dominant sources which can really induce some signal cosmic rays we can see here on this map. And there's one thing that remember that the deflection of the magnetic field depends on the energy and the charge. So if we would have something like a cosmic ray source, it's propagated through the electromagnetic field, we have such patterns in arrival direction because the deflection just depends on the energy and the charge. So we have just very large deflections for low energies and high charges, and less deflections for high energies and low charges. And so we can see such streets or paths. This is something we can look for in the arrival directions. However, this is quite complicated. And if you would like to train a deep neural network on such data distributed on a sphere, we would like to use convolutions. But if we try to use pixel-based CNNs, we directly see that this is a non-Euclidean domain and we need something different. And so the idea is to use graph networks or graph convolutional networks. And there we can just directly perform convolutions on manifolds beyond the Euclidean domains by interpreting the data as graphs. In this case, we use a so-called dynamic edge convolution. So the idea is shown here, that we just use here this continuously distributed data on the manifold we would like to have. And then for each of the, in this case, cosmic rays or particles we use for the next neighbors, in this case, five next neighbors. And then we make a convolution using the difference between here, the central cosmic ray and or this neighbor cosmic ray, these 5 neighbors. And the very nice thing is that this is in fact a kernel in principle when we would interpret it in the 2D image-like convolution, our graph convolution shown here on the bottom. The kernel here is described as a deep neural network. So we basically just can input here to our convolutional operation, which is done using a kernel, this kernel function, and just apply here, for example, give the coordinate of the central particle or cosmic ray, and then the difference between the central cosmic ray and this neighbor cosmic ray. So we can then apply this kernel function 5 times, but for sure we then have to perform one aggregation. So in the normal convolution, this is just the sum, but here we can do a convolution operation and define it the way we want to, calculate averages or just take the maximum. In this case, we just take the average and then we for sure apply activation function. But after the next layer, the nice thing is that we can again search for the k next neighbors. So we have something like dynamic edge convolution, and so the graph we are building by searching for our next neighbors will change in each of these layers, which make it very useful to extract very, very different features. But for sure, remember that these k next neighbors are using something like next neighbor searching algorithm. There's no way to propagate a gradient through this, so we just indirectly map very closely related features during the training of our DNA. And so just a small reminder, so the difference between the convolution and the dynamic convolution is basically just that in the normal convolution we have this discrete filter pixelization, but in this continuous grid positions in our dynamical edge convolution, this kernel function is just continuous function, which is approximated by a deep neural network. But in this dynamical setup, just remember that the neighbors can change, and we have really some very varying setup during the training of the network. And if we now have a look on the architecture, we just put in the coordinates here of the cosmic ray on our sphere and the measured energy, and perform various of these edge convolutions. In the end, a global average pooling, and then can just have a binary classifier saying, okay, this sky map you see here is a signal scenario, or we just measuring isotropy. And if we have a look on this after training, so I think I have to hurry up a little bit. So we just used 1000 cosmic rays with energies beyond 40 eV, and then train it here on these different scenarios. So scenarios with source patterns and without. And if we then have a look on the sensitivity, so we can just check, okay, are we able to really identify that this is a signal scenario or just background? We can analyze 1000 sky scenarios and then just have a look on the median p-value. So the p-value, we are really able to see that this is a signal scenario or not as a function of signal cosmic rays. And for sure, we can see that we have the highest sensitivity as we have more signal cosmic rays. But we can see that depending on the composition scenario, so we have less deflection in helium scenario and the larger deflection, making the classification more challenging for mixed charges. But still, for a pure helium scenario, we would have something like 5 sigma for 18 signal cosmic rays. out of 1,000. So this is quite promising result. And we can still do individual cosmic ray identification. So not saying, okay, this is a sky with isotropy or with a signal source or some pattern we see, but we just ask the question, okay, hey, cosmic ray, are you a signal cosmic ray or are you just a background cosmic ray? And we can see that the efficiency and purity is also very promising, and we can see that dependent for sure on the number of signal cosmic rays, we can see that the sensitivity for helium scenario is quite high, even at 15 signal cosmic rays, but for mixed charges this is way more challenging, but still the efficiency reached 0.7 at the more highest signal cosmic ray. And also the purity is quite promising. We can see that we have for mixed charges and helium, very, very, very nice purity values. So to sum it up, we can perform very deep learning techniques at the Pierre Observatory, and I just use in this case various architectures. So we have recount neural networks to interpret and process time series or time-dependent signals, CNNs to process spatial signal patterns, and graph convolutions to process data on non-Euclidean manifolds. And then there was one approach for using event-wise reconstruction of Xmax, and we saw that we have a very nice performance on simulations and also verified the performance on data, and the expected uncertainties for measuring really the composition using the first and the second moment of the form Xmax distribution are small, and this will give us a rise in statistics of a factor of 10 using VSD, and will or can give us new insight in the composition at the highest energies, because there the flux is just very, very low. And then I was talking about some biases we can see when we train our network on different simulations or on simulations and evaluate it on data, which just looks a little bit different. And there I just showed an approach of an adversarial framework to refine the simulations. And there was just very promising results for this very small scenario. And at the very last point, I show you some application of a graph convolutional network to search for the origins of ultra-high energy cosmic rays. And we saw that for identifying a single source scenario, this is just very high sensitivity. And also we saw promising results for identifying really on a cosmic ray basis, if this is a signal cosmic ray or not. And this is just very promising research. And I'm really looking forward to share with you the new results soon. So many thanks for your attention.
Thank you very much. Oops, that's some kind of effort. It was very nice report. And Ivan has a question, and then there is another question.
Thank you very much for the report. On page 15, you have shown the correlation between estimated Xmax and the measured one. Was it obtained using some particular hadronic model, or you find the one that much better, or what?
So for the correlation, we see that if we use different hadronic interaction models, the correlation is roughly the same, or it's the same because the resolution is basically scales with the correlation scales with the resolution, and we saw that the resolution is independent of the hadronic model. And here we see the evaluation on data, but for sure the correlation just depends on the true composition in data, and also on the energy spectrum for sure we have in data. I hope this solved your question.
Okay, thank you.
And now there is another question from Oleg.
Thank you for your nice talk. You have shown us that you were using also refined simulation, and so with refined simulation you were able to achieve better agreement with data. But can you tell us? Do you have what is the difference between if you use the refined simulation? do you still have a difference in when you are using different hadronic interaction models for your reconstruction?
Oh, sorry, I forgot to unmute myself. So for sure, in this specific setup I just presented here, we just made a hand-designed toy scenario, so not really a detector simulation on top of a hadronic interaction model, but we also tested this on several master theses, and it just looks very promising that you can also, in principle, refine APOS LHC signal traces to look like QGS signal traces, and then you can see that maybe you're shifting the trace a little bit to the right, or the slope, the falling edge just is a little bit less pronounced or more pronounced, just really depending on the underlying hadronic interaction model. But for if you would like to really perform this type of analysis on data, it's very important that you are somehow able to, let's say it that way, are comparing the refine mechanism, the same phase spaces, so that we have roughly the same phase space in simulation and also in data. Did that somehow solve the question or not?
So, I mean, you were trying to obtain the refined simulation, but you did not try to make a reconstruction with this refined simulation, right?
Okay. So in this case, the reconstruction is shown here on the right. So the reconstruction is here based on the DNN, which is trained on the refined simulation. And here on the original, if you train the DNN on the original simulation and applied on the data set, which just use a different hadronic model or different fraction of electromagnetic and muonic particles, we can see with very bad correlation between, or reconstruction between the true energy and the reconstructed energy in this case from the DNN. But if we train it on the refined simulation and evaluate it in data, we can see that the performance increases if we just really compare the reconstructed energy of the DNN versus the true energies. So it's really also the reconstruction.
So my question is the following: your refined simulation, does it depend on the hadronic model assumed or not?
This is really hard to answer, because it depends for sure. It will, if I have different hadronic interaction models and show it and train the refiner to refine one hadronic interaction model to look something like data, the mapping from a hadronic model to data, and I have different hadronic interaction models, will look different. But in principle, my refiner tries to make the hadronic models to look more like data. So after the refinement, the simulation looks more like data than the hadronic interaction model. So the transition function or the refinement function will be different, but the results, even I have, let's say, competing good hadronic interaction models, shouldn't be a big difference between them.
So, but you didn't calculate the difference, right? If you try to use different hadronic models, you would obtain different results, and you don't know precise discrepancy. Right?
Yeah, but the basic idea is that we, instead of performing such calibration, if we have a dependency on the hadronic model, we need some sort of calibration, which we can perform with the FD. Then this would be some data-driven way to just calibrate the DNN to the scale of the data. When we use different hadronic models, it should be expected that this difference will be small.
Yeah, still the main problem with the neural networks. You never know what is your learning sample. Okay, I saw another question. If I do not see the hand anymore. So Dennis, a very short question, please.
Yeah, it was me actually who was raising the hand. So I was
yes,
wondering,
I know.
Yeah, when you were speaking about domain adaptation, right? So you put this data sample with this particular amount of neurons and something here, so the particular cocktail. Did you try to invent any kind of algorithm that will have a better, let's say, that will not react if our model is wrong? So if there is like not 30% but 25%. So if you go to slides before, probably it's in before
that one.
So you have electromagnetic, and so imagine that you're this, and then you in the real data you have 25% to 75%. Would it be? Do you know how to train this kind of domain adaptation?
Yeah, this is really a great and very interesting question, because for sure, in the end, you would like to make your simulation better, right? And not only let the network be better, but understand what's going wrong. And then you have to somehow constrain your deep neural network what is doing. Maybe you allow only shifts and respective scales. Otherwise, you need something to really, use backpropagation through the simulation of Corsica or the shower simulations. But currently, this is maybe very future music, because these, simulations are quite time-consuming. So one shower sometimes needs something like a simulation time of 1 day. So I can't think of. I think the first step toward that would be to just allow the network only small changes and check what's going wrong there, and then try to do it that way. Otherwise, it would be very, very complicated, but for sure, very nice idea.
Okay. We definitely should include time for discussion next time. Oops, still echo. Sorry. Okay, we are moving to the next talk. Jonas, thanks again. This was a great talk.